results. And now let me introduce the speaker. John Grotzinger is a geologist interested in the evolution of surface environments both on Earth and on Mars. He is a mission project scientist for the Mars Science Laboratory, Curiosity. He is the Fletcher Jones Professor of Geological Sciences at Caltech, and previously he has held appointments at MIT and Columbia University. John earned a Bachelor's of Science from Hubbard College and an NMS from Montana State University and a PhD in Geology from Virginia Tech. He has co-authored more than 140 scientific publications and several books and monographs, including 2 widely taught textbooks on geology, I'm assuming. Tell us, I guess. He is the recipient, John has been the recipient of numerous awards, including the Halbuti Award of the American Association of Petroleum Geologists and the Lawrence Sloss Award of the Geological Society of America. John is also a member of the National Academy of Sciences. So please join me in welcoming John Grotzinger to deliver his the 82 Judges Henry Lecture on robotic exploration on Mars's crater, Gale crater. Thank you.
Mission control here. Great. Okay, I think I got this. Okay, so thanks very much for inviting me to come give the presentation tonight. It's a real pleasure. Larry contacted me, I think it was probably the first day after we had landed, and amidst the congratulations we were getting, he asked me if I'd be willing to come and give a presentation. And I replied, and I was eager to do it, but I wanted to wait until we had actually some science data to show you, as well as all the cool engineering stuff that I'll show. And before I get started, I really want to make sure to give credit to my colleagues on the Mars Science Laboratory team. They are 457 science team members at this point, from over 15 different countries and representing 56 different institutions. And my job is to try to manage this mission of exploration and figure out how to get all the scientists, and if you guys know scientists, I think there are scientists here. You know, scientists are independently minded people, and so the goal is to try to share the rover and try to figure out what to do each day, and that's one of our biggest challenges. The other thing about it is that being here in Washington reminded me of a personal experience that I had never had before, which was about 2 months after we landed and we had our first significant science discovery. We were asked to come and testify before the Senate Commerce Committee on what went right. And I realized at that time that where we had our heads so heavily involved in this project for almost a decade, that to everybody else it sort of seemed like magic. And Arthur C. Clarke once said that when technology is so advanced to a person that doesn't understand it, it seems like magic. So we try to go and fill in some of the gaps. And that's kind of what I'd like to do tonight, is to show you effectively what went right here in terms of why this works and why we in this country are so fortunate to have NASA run these missions. I think the first key is that you just simply have to have a grand challenge. If you put 400 scientists in the room and work on a problem that only some of them are interested in, you're going to quickly get people scattering and going in different directions. The coherency of the science team is really imparted largely because we want to look for life in the universe. We want to see if Mars ever had habitable environments. We're trying to take the step that goes beyond just looking for water on Mars. We've done that 1,000 times. Let's go to the next level. The hard part is to do this. And you know, this is one of a handful of rocks on Earth. This happens to be the one that sort of ignited a firestorm of exploration back in the late 60s. A rock called the Gunflint Chert, which is up in the north shore of Lake Superior. And what you can see in here are basically the cells associated with microorganisms that were literally pickled in minerals probably days, when the organism might have even still been living, these microbes. The trick is that if you want to find these things, the chemistry has to happen really early on. So basically, unfortunately, this is not something we can do with this mission. To probably do this, you need to bring rocks back to Earth, and that's where the future planning comes in. So the other person that I wanted to sort of highlight here, and as the evening goes on, I was looking at my room that Larry put me up on the 4th floor, and I saw a picture of John Wesley Powell, who of course helped found this organization in 1969. Here's another very important person in the history of exploration of life on Earth, and this is Roy Chapman Andrews, who was the director of the American Museum of Natural History in New York. And what he's doing here is exploring in Mongolia for what were some of the early dinosaur finds. You've all heard about dinosaur eggs. Well, he's the guy that discovered them, and we'll come back to that later tonight, and you'll see why. But this is what goes on in the early history of exploration of the Earth. You wind up going out in the middle of nowhere, in this case with a relatively small number of people, and you're exploring and trying to come up with a paradigm that once you find a trace for something, you want to follow that trail. And so that's what we're doing with Curiosity, and amazingly enough, we're only just getting started. This mission could easily go on for a decade. The other thing about it is that the engineering has to meet the science challenge. And so we had, over 6 years, 60 different candidate landing sites to explore on Mars. And in the end, we had to just come up with one. So we met twice a year. Anybody in the world could show up and advocate a landing site, present its attractive attributes, and try to sell it to the crowd, about maybe a little bit more than the folks in the room here. And all the scientists then preside over this, and they decide whether or not this story holds water or not for how attractive the landing site is. And then eventually you have the final 4, and then we go away and try to pick the last one. However, 2 years before this, I was told by my colleagues at JPL, oh, don't worry, you scientists are going to find your favorite places, but when we actually try to fit it into a landing ellipse, they're going to go away because it's just going to be too dangerous to land there. Well, it turned out because of the extraordinary effort in engineering, we were left with 4 sites to pick from. And so basically, instead of the engineers taking them out of the action, the scientists were left to kill each other and try to figure out which one we were going to pick. And this is the one that we picked. To give you a sense of scale, here's our landing ellipse. And it has this shape because when the spacecraft is approaching, it has this trajectory. So the error in its position is more likely to be uprange and downrange than it is across range. That's why we have an ellipse. And the center of the ellipse is right about here, and this is where we landed. So we were slightly off of center, and that would be equivalent to teeing off in Tokyo, aiming for the Empire State Building, and missing by 1/5 of the building. That was the accumulated error that took us to Mars. But the key is that this landing ellipse, we were able to snug it into this moat that goes around between the crater rim and this mysterious mountain that exists here in the middle, which was so attractive to us. That was really the engineering feat. And the scientists basically said, that's where we want to go. And then it was up to the engineers to get it there. And they needed a grand challenge as well. And they pulled it off. So we're interested in landing and then exploring the lower reaches of what we call Mount Sharp over here. And I'll talk about this later. But first, let me take you back and do a little rover history here to give you a sense of where this all comes from, because history and pedigree are very important in the engineering business. So back in 1997, 4th of July, we land the Sojourner rover on the surface of Mars. It rolls off of Pathfinder, which was given that name because it was finding the path forward for NASA's future exploration mission. And what it did is it had 3 challenges. The first was to better, faster, cheaper. So we were working with an economic model where the funding was lower. We didn't have the amount of money we had during Apollo and Viking, so you had to get to the surface and develop a science platform, but get it there as cheaply as possible. So you might remember that these first-generation rovers landed in airbags, so they were basically collapsed into a tetrahedron, then with airbags all around it, and then the parachute deploys and it decelerates the spacecraft, and then at some point you wind up with a velocity that's low enough that you can just cut the cord and bounce to the bottom, and then you just skip along and dissipate all that energy just by sort of soft crash landing. The other thing that we did then was to experiment with a rocker bogie six-wheeled suspension system here that allows the rover to drive over an object as big as the wheel without tilting the deck of the rover very much, because it's a solar-powered rover, and we don't want to get severe tilts because suddenly you might lose your sunlight and then you're stuck. And then the other thing was to put on a little bit of science on the front here, and so we'd roll around and look at rocks like this and measure their chemical composition. But NASA considered this to be what's called a technology demonstration, tech demo. And this way, if the mission failed, it's not mission failure. It's actually a technology demonstration that you were sort of taking a crack at, and if it doesn't work, you don't suffer the damage of a failed mission. However, it worked, and so then we went to the next level in the next decade, and here you have Spirit and Opportunity. You see the heritage of the very successful mobility system. You see the heritage of the solar panels up here. And in addition to that, now we've got a mast on the top with cameras and an imaging spectrometer. And in this case, this rover didn't go much farther than the area of the platform that I'm standing on. And the lander took pictures of the rover scooting around doing its thing. In this case, the cameras go with the rover. You land on a platform, the pedals unfold, the rover drives away, and that's how the mission of exploration begins. The goal of that mission scientifically was to look for evidence of water on the surface of Mars that was predicted to be there based on all the orbiters that have been going around since the late 60s and 70s. Could you actually measure a property of the rock that would show that there really was water on the surface of Mars, and that water was the liquid that created all those cut channels that you saw in those ancient landscapes? And the answer was yes, and since that time, Spirit and Opportunity were built to last 3 months and drive 300 meters. Opportunity is now going on 9.5 years, and it's gone over 30 kilometers. That led in the next decade to Curiosity, which is where we are now, which is a mobile chemistry lab. The big difference here now is that we just scale it up because we've got a lot packed in here to analyze the composition of the surface of Mars. And the question we're asking now is not just whether there was water. We'd like to find evidence for water really early on, and that was a mild celebration in the team. There's no more jumping up and down just because we found water again, because we took a landing site where we figured there was a high chance that we would actually find it. What we want to do now is understand the ancient chemistry of that water. We want to try to understand whether this was the kind of environment that if a simple microorganism was living there, it could actually sustain itself. That's what we mean by habitable environments. Was there evidence of carbon, hydrogen, oxygen, nitrogen, phosphorus, things like that? Were there redox states presented in the minerals that would allow them to do metabolism? Those were all key things that we're after here. Okay, and then this mission, I'll just mention quickly, paves the way for the future in the next decade. NASA announced after our successful landing about 2 months later, they said they want to now develop the next rover mission, 2020. It will launch, and it will be a precursor for what will then hopefully be a mission that collects samples, caches them, and then delivers them to a vehicle, what's called the Mars Ascent Vehicle, which sends them back to Earth. So that's what's in store for the next decade. Okay, so here's Curiosity, and it's got the most ambitious science payload ever sent into space anywhere, including the moon. And there are 9 principal investigators who have built 10 instruments. And I'm not going to go through all these in great detail because this is a general audience, but if people have more technical questions, feel free to talk to me afterwards. I'll break them into 3 groups. Begins with remote sensing. Can I see those curtains across the room there? And if I do, can I tell what kind of fabric they're made out of? So the cameras tell me that I've got something that looks familiar, but I don't really know what the material is until I get a little bit closer, and then I use this laser to reach out. Goes out about 7 meters out in front of the rover, and then it basically burns the rock, or the soil if that's what we're looking at. Creates a plasma. We gather the light in a telescope, send it down a fiber optic cable, and it goes into some spectrometers on board the rover, which then tell us about the composition of this rock in kind of a qualitative way. We get a sense for it. If we like the rock, then we drive up to it and we get the arm out here. Now this arm works like ours do. It has 5 degrees of freedom, okay? So it does all the motions that we can do. And so we can get these instruments down here. And one of them gives us a much more precise measurement of the chemistry. This one up here is a hand lens, color, HD resolution, makes videos if sand grains are bouncing along. And then if we decide we really like the rock, then we put the drill down, and here you can see the drill bit. We drill a hole into the rock, collect the powder, pass it back into some sieves in here. You know, just think of a flour sifter. That's kind of basically how it works. And then it passes through the sieves, and we get the finest grain fraction, take the arm, bend it over our shoulder, and dump the sample into the belly of the rover, where it goes down into these 2 instruments down here. That, again, I'll just describe a little bit more when we go along, because I don't want to get into too much detail here. Here's what's under the hood. Take Curiosity, turn her upside down, take the belly off, and here's what you've got. This is the biggest instrument that we carry, and it has three different instruments, all packed in one. And at Caltech, my colleagues would have 3 different rooms, each one with one of these instruments in it. But you take all those 3 different rooms and you miniaturize it. Take 10 years to figure out the technology to miniaturize it. Put it in something the size of a microwave oven, and it only costs you $90 million. This one over here, this is one that normally would sit about the size of a dinner table. It's X-ray diffraction unit, and that we shrink down to the size of a toaster, and that only costs you $20 million. But that gives you definitive mineralogy, and this is one that actually has been able to become commercialized. And the Getty Museum bought one of these things, and it actually uses it to aim at the artwork. And if you want to know if the art is changing its composition through time, it will actually tell you that in a non-invasive way. Just quickly, some other interesting little facts about Curiosity. This rover cost $2.5 billion. This time we don't get 2 of them. So we mitigate the risk of failure by having redundant spacecraft computers. So we have an A side and a B side, and normally what we do is we've got an emergency computer, basically. If something goes wrong, we swap to the other one. Otherwise, more uneventfully, we upgrade operating software. And we just simply drive off of the A side, upgrade the new flight software operating system to the B side, then swap over to the B side, run the rover on that for a while, decide that it works well, then we wipe the A side and write onto it the new operating software there, and off we go. So every once in a while we do that with the rover, just like we do here on Earth. Rover motor controller, we've got 39 motors, and this basically shunts the power to those motors. Power electronics down here, this basically just buses the power all over the rover, anything that needs to be powered. That's how, these are all the circuit boards down here. Power is generated by a device that's missing right here. It's a thermoelectric generator, nuclear powered, plutonium-238 source, generates heat. We have thermocouples wrapped around that thing. It converts the heat to electricity, and we generate about 100 watts. So it'd be like turning a light bulb on for 24 hours. That's about how much power we generate each day with that. And just like at Cape Canaveral, when the last thing that happens on a human mission is the astronauts get in and then they close the hatch and off you go. In this case, just because of risk management, the RTG is the last thing that gets installed in the rocket, close the hatch, then off we go. We have batteries, lithium-ion batteries, because even with this thing cranking out 100 watts, that's not enough to drive these. So to do an experiment, we have to basically draw from the batteries to run these instruments and do the most energy-intensive operations. And then we've got a couple of radios that I'll talk about later. And then here's our thermal fluid loop. Just think of a radiator. It takes the heat from the RTG, circulates it around the interior of the rover, because at Mars at night it gets down to 100 degrees centigrade, and we got to keep Curiosity above minus 50 degrees centigrade. So that keeps the rover warm inside. This may be the most important lesson learned for why JPL is so good at doing these missions. It's a little bit like you've heard the real estate expression, location, location, location. In this business, it's basically test as you fly and fly as you test. And you do not do anything unless you have fully tested everything that you're going to do on Mars, and you don't build anything that you can't test. So if you have a wild idea, you get a certain amount of time to make it happen, and then after that it's off the table. And then once you get hardware, you don't fly it to Mars unless everything's been tested. So this is one of our more interesting tests, because what we've done now is take all the subsystems and put them together into a single system called a rover. And then we basically emit from a light source solar radiation that would be equivalent to the sun shining on the rover on Mars, because this thing is basically made out of a ton. It literally weighs a ton of aluminum and titanium, and some plastic as well in there. But the important thing is that with 100 degrees centigrade variation in the temperature every day on the surface of Mars, this rover is expanding and contracting. And if you're drilling a rock and the arms out there at the end of the rover, you're going to tug on it by about 1.5 centimeters. You're going to go back and forth with the rover each day, just by all this metal expanding and contracting. So this engineer has basically got this wand. They're wearing white so they don't contribute any heat contamination. The end of the wand has a sensor, and basically the engineer is touching the different parts of the rover and measuring the actual temperature compared to what a supercomputer is predicting that the surface temperature should be of the rover, because at the end of the day, the way that we do the most sophisticated testing is with computers. So we get some physical verification of this. Take the rover, verify it, it goes back to the lab, all the parts come apart, we test all the subsystems, put it back together, send it to the same facility, test it one last time, then we're good to go, and we ship the rover off to Cape Canaveral. It gets installed into an Atlas 541 launch vehicle. That's kind of the standard rocket that they use to put satellites into low Earth orbit and also send stuff into outer space for science. And it was a beautiful day, November 2011. It was supposed to have been Thanksgiving Day, but we had an issue with our battery that we wanted to double check, so we delayed a day. And everybody else out was shopping, and we were launching rockets. It worked well. We had a period of what's called cruise for about 8.5 months that takes us to Mars at the interplanetary velocity of about 13,000 miles an hour. That's how long it takes to get to Mars. And then we had this amazing sort of 7 minutes of terror, as the public came to know it as. How many people have seen the 7 minutes of terror video? About half. I'm going to show that in a second, but let me just point out some of the key things that will go by quickly that you should pay attention to. And there are enabling technologies here that allowed us to get into that moat. And the most important of which is that there's ballast, what's called the aeroshell. We basically dissipate all its kinetic energy, interaction with the upper atmosphere, frictional heating. But as we're doing that, we kick out some ballast in the front, and that tips up the edge of the aeroshell, and it flies like a wing. It actually has lift. And then you'll see thrusters. In NASA speak, it's called a reaction control system. And all these, you'll see these rockets shooting on and off, and basically the onboard computer, which has an inertial navigation system, has been pre-programmed where it should land on Mars. It's computing the real-time errors that are accumulating because it's not going to that point, and the reaction control system is telling it to fly back in this other direction. All in real time at very much hypersonic velocities. And so then we decelerate down to about, down to a little less than Mach 2. The parachute, before the parachute deploys, you send the ballast out on the other side. So you restore the center of symmetry to the center of mass, so you don't get some crazy two pendulum problem going on here when you start yanking on the parachute. The heat shield deploys, a radar turns on, the powered descent vehicle ejects from the aeroshell, starts flying out on its own, and then it basically dangles the rover down. We call it rover on a rope. And it allows the rover to touch the bottom. And then as soon as the rover touches the bottom, the computer on board here, the propulsion system recognizes that the force balance has just changed because now half of the mass is actually supported by the ground on Mars. And when it does that measurement 5 times in a second, and then it cuts all the cables, the descent stage goes off and crashes, and the rover is pretty much ready to go. So just keep your eye out for that. And the last thing I'll say about this video is that we believe that this had a lot to do maybe with the popularity of this mission, because NASA did something it had never really done before. There was a guy who would make videos for media relations, worked for 25 years for JPL, And then he decided he just wanted to go off on his own and do something a little bit different. So he got these engineers alone. You'll see all the lead engineers here. And he got them to basically talk about what they thought were the greatest vulnerabilities. And when, at the end of this thing, you can't believe it's going to work. I still watch this thing. I've never been bored watching this thing. And what happened was there was not really a clamp down to try to prevent this thing from coming out, but it was not met with a lot of initial enthusiasm because people said, geez, if we crash, everybody's going to know why. And, and what we told the media relations people was, well, they're going to know why anyway because everybody's going to be testifying back here. So in the end, they decided to release this thing, and before we landed, it already had 80 million hits. And then within 48 hours of landing, the server crashed, NASA's server crashed, and in the end, it turned out there were over 1 billion hits of this video. Okay, so we'll take a look at that.
When people look at it, it looks crazy. That's a very natural thing. Sometimes when we look at it, it looks crazy. It is the result of reasoned engineering thought, but it still looks crazy. From the top of the atmosphere down to the surface, it takes us 7 minutes. It takes 14 minutes or so for the signal from the spacecraft to make it to Earth. That's how far Mars is away from us. So when we first get word that we've touched the top of the atmosphere, the vehicle has been alive or dead on the surface for at least 7 minutes.
Entry, descent, and landing, also known as EDL, is referred to as the 7 minutes of terror because we've got literally 7 minutes to get from the top of the atmosphere to the surface of Mars, going from 13,000 miles an hour to 0 in perfect sequence, perfect choreography, perfect timing, and the computer has to do it all by itself with no help from the ground. If any one thing doesn't work just right, it's game over.
We slam into the atmosphere and develop so much aerodynamic drag. Our heat shield, it heats up and it glows like the surface of the sun. 1,600 degrees.
During entry, the vehicle is not only slowing down violently through the atmosphere, but also we are guiding it like an airplane to be able to land in a very narrow, constrained space. This is one of the biggest challenges that we're facing, and one that we had never attempted on Mars.
Mars is actually really hard to slow down because it has just enough atmosphere that you have to deal with it. Otherwise, it will destroy your spacecraft. On the other hand, it doesn't have enough atmosphere to finish the job. We're still going about 1,000 miles an hour. So at that point, we use a parachute.
The parachute is the largest and strongest supersonic parachute that we've ever built to date. It has to be able to withstand 65,000 pounds of force, even though the parachute itself only weighs about 100 pounds.
When it opens up that fast, it's a neck-snapping 9 Gs.
At that point, we have to get that heat shield off. It's like a big lens cap blocking our view of the ground to the radar. The radar has to take just the right altitude and velocity measurements at just the right time, or the rest of the landing sequence won't work.
This big, huge parachute that we've got, it'll only slow us down to about 200 miles an hour. And that's not slow enough to land. So we have no choice, but we've got to cut it off and then come down in rockets. Once we turn those rocket motors on, if we don't do something, we're just going to smack right back into the parachute. So the first thing we do is make this really radical divert maneuver. We fly off to the side.
Diverting away from the parachute, killing our horizontal velocity and our vertical velocity, getting the rover moving straight up and down so it can look at the surface with its radar and see where we're going to land. And we head straight down to the bottom of a crater, right beside a 6-kilometer high mountain.
We can't get those rocket engines too close to the ground, because if we were to descend propulsively, with our engines all the way to the ground, we would essentially create this massive dust cloud. That dust cloud could then go and land on the rover. It could damage mechanisms and it could damage instruments. So the way we solve that problem is by using the sky crane maneuver.
20 meters above the surface, we have to lower the rover below us on a tether that's 21 feet long and then gently deposit it on its wheels on the surface.
As the rover touches down and is now on the ground, the descent stage, it's in a collision course with the rover. We must cut the bridle immediately and fly the descent stage to a safe distance from the rover.
So it worked. Adam, Anita, and those guys, they were immediately unemployed and very happy about it. And the science team had to go to work at 10:39 p.m. Pacific time. And this is the first data that we got. The image that you see on the left was the one that came down 10 seconds. So if you were watching, there were people jumping up and down in blue shirts. And 10 seconds after we got confirmation of landing, the sky crane has gone off and it crashes about a kilometer away after about 6 seconds of flight. And then after 10 seconds, we take pictures with the hazard avoidance cameras that are down low on the rover. And you can see that the dust covers have worked, which is good. And you see the shadow of the rover because we're landing in the afternoon. And we thought we saw the thing that we had come for, which is this mountain looming in the background, but we couldn't be sure. And anyway, so then you wait 2,000 seconds until the next image comes down because you told it to wait, whatever it is, 39 minutes, something like that. And now the dust cover has deployed. And that was really a big moment because that means now we have a driving mission. You could probably drive with this much schmutz on top of these covers here, but it would be kind of dicey with the hazard avoidance algorithms. But here you got a nice clear view. Shadow's a little bit longer because 39 minutes have gone by, and what you do is you get your first look of Mount Sharp, which rises 5 kilometers above the base here, so this mountain has more relief on it than any mountain in the lower 48. It's even taller than Mount Whitney. So the science team went to work, and we work at night, and I'll say a little bit more about that later on. We work at night on Mars. We stay synced to Mars. And the next day, we got more data down from the orbiters that had been collecting information, and what we realized was that was that the world was watching, and unlike the other rover mission that I worked on, people pay attention to this one, and they get their money's worth. You know, I mean, the taxpayers are underwriting this, and they are having fun, and you can find lots of nice stuff on the internet. We then stood the antenna up. We stood the mast up. And we began to take pictures. And we do a 360 first with the navigation cameras. And you can see the crater rim, which we suddenly realized, gosh, that's a pretty impressive mountain range in its own right. We had been fixated on the Mount Sharp in the middle there. You get to see what Anita Sengupta was talking about, where during the sky crane maneuver, the reason we've got the rover dangling down on a rope is because we're so worried about the thrust from these rocket engines. If they get even closer to the ground, they're going to have even more force, which is going to send stuff flying. You can see the holes that they blasted through the soil, and some of that material actually did wind up on top of the rover here. You see scattered pebbles there. Fortunately, we didn't sustain any damage, but you can believe that it was definitely the right risk trade-off to have done the sky crane to avoid what surely would have been much higher velocity impacts that might have damaged the rover on landing that way. So then we start taking color pictures, and now we start to get the view of Mars we've never seen before, because every other time we've landed, the engineers can only get us into these big gigantic ellipses, and that means we have to have a super flat place to land on. And you might see something in the horizon, but here now we've got this crater rim. With our telephoto lens, we can zoom right in on it. And there's as much relief here as there is if you go out to the Mojave Desert. If you've ever been out around Las Vegas, you drive between Vegas and LA, you see these mountain ranges going up, little LA smog coming in here. It kind of made us feel like home. I mean, it doesn't look like weird Mars. This kind of looks like where I take my students out for training trips. And you see what the ancient river valleys that have cut down through the mountains. And you can see strata out in front of them here where the sediments gathered that were derived by erosion of these mountains and transported water out here. And you can begin to not actually really have to use a lot of imagination to once imagine the water that might be here. And so we were itching to go. And then we got the rest of the image down the next day, looking back towards Mount Sharp, and that looked even better. And, it's a spectacular terrain. And someday we'll go here, but basically you're looking at buttes and mesas that have a couple hundred meters of relief on it. It's kind of terrain that looks like it's something out of a John Ford movie. Almost expect to see a stagecoach with John Wayne cruising along here. And, but this is where the action is for us, at least that's what we thought based on orbit. And therefore, it came as a great mystery to the media when the science team decided to drive in the opposite direction. And go look at some rocks that we realized we landed very close to after we had been telling them for 2 years, we're going to go here, we're going to go here. And so off we went, and the first thing that we did was we commissioned one instrument after another. And it took me a while to get the hang of this. I mean, you can't believe this is actually going on, and now the science mission is real. And the biggest mistake you could make is to rush and make a mistake. Because what has happened is when that thing has landed successfully, you have deployed a priceless national asset to the surface of Mars. It's not obvious we're ever going to do this again. With the budget situation that we live in these days, it would be really hard to pull off this mission again. So we want to take care of it and preserve it for the next generation, and maybe some people in here will have the chance to work on it someday. So we test each thing out one at a time, and we make sure that it's really going to work well. And when we operate it, that the robot did exactly what we told it to do, no more, no less. And if there is more and there is less, then we stop and take a look at what happened. So we wanted to test out the laser. Everybody was really excited about this laser. What's it going to do? And so we looked around, and the Sky Crane's radar did a really good job of keeping us away from any interesting-looking geological terrain. So we wound up on normal Mars gravel terrain, and we looked around and we found the biggest rock, which is about the size of a hockey puck, and we discussed it for a while, and we decided to take a shot at it. So here's what you get. If you take a picture after you acquire this kind of data, we commanded an array of 4 spots. So here's the first one up here, and it basically drills a little hole in about 1 millimeter in diameter. And again, I'm not going to go into the details of the science, but what we get out of that is the composition of this rock. Then we did a second one here, and a third one here, and the fourth one actually produced a little explosion. And so you can see that this looks different than the other 3 here. It must have been a little bit of a pop there. And so we think maybe there was a vesicle that might have had some water in it or something like that, because hydrogen is very likely the material that would have produced the explosion. We're not really sure what that means, but I can promise you, we've done this now thousands of times. That's the most exciting thing that we've ever done. But this is what the world thinks we're doing. And it's those same guys with transformers. They're having fun again. And there's others I could show you, but I probably shouldn't. But curiosity and cats, you can sort of guess what goes on. Okay, so here's what happened when we drove in the opposite direction. The crater rim is over here. Mount Sharp, the foothills of Mount Sharp, this is what those buttes and mesas look like, these little nubbins that you see down here. We're supposed to be driving this way. We land here, we're supposed to be going this way. Well, we went in the opposite direction, and the reason why is because of this red stuff. And again, I'll just give you the simple version of it. It's a rock property that we call thermal inertia. It's the ability of a rock to retain or give up its heat. And so what's happening here is that at night, there's an orbiter that flies over Mars, and it takes pictures of the surface in the thermal part of the spectrum. And it looks for stuff that's glowing, giving its heat off later on in the day. And that's what's going on here. So what's interesting to us as geologists is that water flows downhill. It comes out of the crater rim. It spreads out into this thing called an alluvial fan, which is just a sedimentary deposit where the flow of water just sort of spread out like that. But out in front of it, we've got all this red stuff. We've got some kind of material that has high thermal inertia. And so our hypothesis is that maybe this is cemented rock, and the rock is harder than anything around it because there's minerals in it that formed in water. So it's an investment of 500 meters in the opposite direction, but again, it took days to clear this up with the media. Nothing went wrong, there's no strange plan going on here. It's just scientists being discovery driven and wanting to take the risk of a short drive in the opposite direction that could have paid off with nothing interesting versus maybe discovering something very early on in the mission, which then lowers your total mission science risk of never achieving the thing that you built the rover to find. So there's a trade-off there. Okay, so what's it like to drive the rover? I get this question a lot. It's not an Xbox. We don't joystick it. You're not sitting there looking at the pictures, because remember what Adam Stelter said, distance between Mars and Earth is far enough that even at the speed of light it takes 14 minutes. So the rover's going off the edge of the platform. By the time I see that, it's been down and gone for 14 minutes. And so it's all done autonomously, and we send command sequences back and forth, and it really does work as a robot, even though sometimes it almost seems human. Here's how the communications work. There's two radios that we use to basically communicate with the rover. Very simply, we have a UHF radio here, and that has a very high bandwidth communication with the orbiters that are circling around Mars. And we send most of our data to these orbiters because they have big antennae and they have powerful transmitters, much more powerful than anything we've got on the rover here. And so what that means is that we can store data up here, and then when it's your turn to send something into the 70-meter dish in Madrid, Spain, and every other mission has stockpiled their mission and they're all aiming for that antenna, you get your shot to send down your data. You wait in a queue until it's your turn to get data back to Earth. The way that we actually tell the rover to do things is via an X-band radio that is basically on a U-joint that allows us to turn this thing that looks like a satellite dish in any orientation. So if we've driven somewhere, we don't have to worry about parking the rover in the right direction. We can park the rover in the right direction for science, maybe to put the arm out and do something, while our antenna turns away and it looks in the almanac that's stored on board for when Earthrise should be happening, and then it basically sends the data back to the Earth, to one of these 70-meter dishes, Madrid, Spain, out in the Mojave Desert, the other one's in Canberra, Australia. So if we need to communicate with the Earth, Earth always has an antenna that we can see. And then when we communicate to the rover, in the morning on Mars, we send a command sequence and uplink it directly to the rover and tell the rover what to do. So it's kind of like email messages. One just after sunrise on Mars that we send to the rover, and the other one we get from the rover just before sunset on Mars. Then the science team goes away and we work on the data while it's nighttime on Mars. And that gives us the most amount of time to think carefully about what we're doing. So basically, Mars, the problem is though, Mars rotates once every 24 hours and 39 minutes. That's really annoying because you have to follow that 39-minute every day. It's like getting in an airplane, flying 3/4 of a time zone, then stopping. Then the next day, you fly another 3/4 of a time zone. And so we track that, and what happens is, in my case, when you live in Pasadena, you think you want to see your family wants to see you. In the end, what happens is you're coming home at 4 in the morning, you're cooking dinner at 4 in the morning, the kids are getting up at 7 o'clock in the morning to go to school, they're waking you up, and after a while it just became obvious I needed to go rent an apartment. So you go in there, go to Michael's, get the black cardboard, cover the windows, and basically we did that for the first 3 months of the mission. And the reason why is because we want that 16 hours every day to think carefully about what we're doing. Then as we get the hang of it after a few months, then we no longer follow Mars anymore, and we go back to a 14-hour workday, then we pare it down to 12, 10, then actually we don't work on Sundays anymore, and now today, for the first time in this mission, we're not working tomorrow, we're not working Saturday. So today, we uplinked a command sequence from Goldstone out in the Mojave Desert to the rover that told it what to do for 3 days in a row. And it will operate autonomously without humans in the loop. This is a huge thing for us because you start to get a social life back again. Okay, so here's an actual, this is data that was downlinked to Earth that we, then the guys with the software, it's called RSVP, make an actual movie of what the rover did. So we have the actual terrain maps. The rover was commanded to drive forward 3 meters, turn its wheels, do an arc turn in place, and then back up 1 meter. And what you see happening up here is that the cameras are always swiveling around to take pictures of the wheels and the terrain, because we want to see what's happening. We want to see the interaction between rocks and soils and the way that the cleats are behaving. And most importantly, we want to calculate the percent slip. So what we do is we want to drive 3 meters. We tell the wheels to turn the certain number of revolutions that are required to give you 3 meters. But then afterwards, we get the actual, and usually it's less because the wheels are actually slipping as they turn against the soil on Mars. And it's really important to get that right, because that way you don't drive into things you don't want to drive into. Here's the actual data. That last time that you saw the camera head move around and take a picture at the crime scene of where it had just driven, this is the actual data. We have the 4 blast marks that were made by the sky crane. You see the wheel tracks advancing forward 3 meters, arc turn in place, and then go off at 90 degrees, turn the camera head around, take a picture. And for the first time in human history, we don't see a lunar module that the astronauts walked out of. We see tracks instead of footprints. There's no lander that Spirit and Opportunity rolled off. It just looks like the thing almost dropped out of the sky. And you know, that's the way these missions are going to be done from now on, when you need to get 1 ton of hardware onto the surface of Mars. Okay, so now getting a little bit more into the science, let's go up into orbit and take pictures of our landing site. Here's Curiosity, which you'll remember from the previous pictures, is white. So it has a very high reflection that you can see from orbit. And then this dark area that you see here is where the dust was blown away by the thrusters, pushing all the dust away. And you don't have to be a geologist to recognize that if you look at this picture, there's basically 3 different types of terrain here. There's this terrain that we landed in that, you know, kind of looks hummocky. So we call it the hummocky terrain. And then you got a terrain over here that has a whole bunch of impact craters in it. Kind of looks like the moon. So we call it the moon terrain. And then we've got something up here which has very few craters in it, and it's light-toned. So we call it the light-toned terrain. And what we know, this is the thing we had to explain to the media, if you just drive a couple of football fields in the opposite direction, you get to go to a place where all 3 of these terrains come together. That's a geological jackpot. That's what we're trying to do. That's like doing a jigsaw puzzle and going for a corner. We got a corner here. And you know, we're going to work on the edges next. So basically, we were after this material because this is what we saw from orbit that had the high thermal inertia. And when we landed and looked towards the crater rim, that's where we saw the layering and the strata here. And that's what we're after, is the strata. So while we were driving along, we got about halfway across. There's a little bit of a rise here. And as we were coming up on that rise, we actually found some rock outcrops. And this is what they looked like. The thing on the left is from Mars, and here's an analog from Earth. And what we saw on Mars is something that basically looks like an urban construction process. Somebody came along with a jackhammer and lifted up the sidewalk. You ever looked at the chunk of the concrete and cross-section? It basically looks exactly like this. That's what this is. It's practically concrete. We have rounded pebbles in a matrix of something that got cemented in hard. Here's a rock from Earth. It's exactly the same thing, rounded pebbles in a matrix of something that made it cemented in hard. That's how sediments become rocks, by interacting with water and minerals precipitate. The important thing is that it's a rock, that it's cemented tells you there was water, but the fact that the pebbles are rounded tells you that there was a lot of water and it flowed for a long time. Basically, this is an ancient stream bed. The difference is this one on Earth is 1 million years old, which is not that old for the Earth. But this one is 250 million miles away and over 3.5 billion years in age. I can tell you that is probably the most ancient stream bed you'll ever see in your life, because we don't think these things exist on other planets. Okay, so this is where we found that interesting stream bed, and then after that we kept cruising downhill. Now we're going to go with the flow. We're going to follow that ancient stream bed and see where it leads us, maybe into a lake. So we kept going downhill, and as we went along, we took a time out actually at this place called Rock Nest to sample some sand. And I'll spare you the details of that and just show you kind of a cool picture. It was our first self-portrait. So what we do is we hold the camera that's on the arm out like this, And we take 57 frames in all the different positions that gives us this view. And then we just move the arm over just a little bit, and we take a couple more pictures where the arm was, and then we Photoshop it in. So if you look at the picture carefully and download it from the web, you can see the splice over here, but it looks like somebody walked up and took a picture of the rover. The science thing that we did was to take the arm out, which you can't see in the view here, and take 4 bites out of the soil here. We took that stuff, put it in the rover, shook it around, cleaned out some hardware, and we did some analysis, but I won't tell you much about that. We wanted to keep going. We wanted to go find that stuff that we saw from orbit. And we eventually got there, and this is what it looked like. And suddenly Mars goes from being the kind of barren plain that we're used to seeing with lots of gravel and sand floating around to basically pure bedrock. And it looks like the kind of bedrock that you'd find in Moab, Utah. It looks like a great place to go mountain biking. You got these whalebacks over here and stuff like that. The thing about it is it's all rock. And for us, that was a really good thing. And we could also see these layers in it. And the layers are important in geology because they're like the pages in a book. You start with the layers that are down at the bottom, and those are the earlier chapters in the book. And then as you go up through the progressively higher layers, you read later chapters in the book. You don't know what the story is going to be, but in our case, we were hoping it was going to be something about habitability. So we already had the evidence for water, and then it turned out we found more. As soon as we drove into that terrain, the whole world changed. And now we've got a rock, which is really fine-grained. It's like mud-sized material, but it's cemented hard. It's shot through with these fractures. If you've ever been on a tour to a mine district and they take you around and show where the miners were picking at the rock, they're looking after veins. Everybody's heard that expression. You know, the old geologist is looking for veins. On Earth, we're looking for quartz veins that maybe have gold associated with them. But here on Mars, what we found is our equivalent of gold, which is a mineral called sulfate that has water in its structure. So we know that we've got water flowing across the surface, and now what we see is an ancient fracture network with water, groundwater, flowing through this, precipitating minerals in here as well. That was really key for us. So we began to feel good about this. We drove around a little bit more, made some more measurements, and then decided this would be the first place that we would ever drill a hole in another planet. And here's our drill hole here on the right. But what's kind of good to do for a general audience is to compare it with what we did a decade earlier when we landed Spirit and Opportunity. Here's a kind of a hole that Opportunity made. We didn't have the technology to drill then, so this would be like taking a piece of sandpaper and just swirling it around for about half an hour until you ground into the rock. And what you can see here is that on the sides of the area where you grind it away, you produced a red powder, and the rock itself looks red. And we know that Mars is red. And the reason it's red is because it's got iron. And the reason the iron looks red is because it's all been oxidized. And I won't go into more detail than that. But that's an important thing about Mars. There's a lot of oxidized iron. So here we have a rock that we know from our chemical analyzers has iron in it. And that iron is all oxidized. So ancient Mars kind of looks like modern Mars, which we learned from Viking. You know, we're not sure it's a complete bummer, but it is definitely not a happy situation for microbial life living on the surface today. Instead, when we drilled down into this rock down in that little valley there, we got gray Mars, grayish green. And this was different. This was something we had never seen before. Now here's a couple of rocks that come from Earth. And I'm not sure there are that many brownstone buildings here in DC, but you go to New York, Boston, they're all over the place. The brownstone is basically this stuff. It comes from quarries in New Jersey and Connecticut, and it comes from a rock that's cemented by minerals that have iron that's been oxidized, and that's why it's brown. It's basically a reddish color brown, doesn't make any difference. But the key thing is, from the same quarry, this is an ancient river deposit. You go to the same quarry, you get gray stone, but people don't like gray because it looks kind of drab, and you know, Boston's not the sunniest place, so let's have some color. But the gray stone was deposited in the lake that the ancient river flowed into. And so what we're doing is that here we had evidence for water flowing across the surface of Mars, but we never found the lake that went along with it, and here we basically drilled right into it. So that's what we think happened, is that we found a place where the water accumulated and not everything got so oxidized like we had been used to seeing in the past. Okay, so you drill the hole, It goes into all the sample processing stuff that I haven't told you much about, but this is what comes out in the end. This was the happy day for us because we knew that not only did we make a hole, but the powder corkscrewed its way up through the drill, went through the sample processing system, went through all the sieves, and came out in the end into this scoop. And so then from the scoop, we're able to collect a portion of it and drop it into the instruments. And I won't go into the details of that, but basically what we learn is the reason that the rock was green is because it has clay minerals in it. And this was something that we were desperately hoping we'd discover sometime. They're not just in there, they make up 20 to 30% of the rock. So there's a kind of a rock on Earth called shale. If you heat it up a little bit, you get slate, which is the stuff you make roofs out of. And this is important because clay minerals only form if it's a neutral pH environment. The minerals that we saw in that rock from 10 years ago all formed in very, very acidic environments, probably pH 1, maybe even pH 0, something like that. So we know we've got a normal pH environment. The other thing about it is that the water was very low salinity. The rock we analyzed 10 years ago, the salinity was so high that it was like honey at home on your shelf. And the reason that the honey never spoils is because microbes, even if you drop them in there, they can't live because there's water there. We found water on Earth in a honey jar, but the problem is that water is useless for life because it will suck the water out of the microorganisms rather than the organisms deriving some benefit from the water. So it's really acidic, really salty, and the other thing about it is everything's oxidized. And the only way I can explain the oxidation thing simply is to think about a battery. Got a positive end and a negative end. Some types of microorganisms are like batteries, and if you put them next to the right minerals that are oxidized to various degrees, the electrons flow. And just like the battery will turn a light bulb on, the rocks, this stuff on Mars, if there had been microbes there, it would turn the microbes on. And we found carbon. And so you put it all together, and we found the first habitable environment that's ever been discovered away from Earth. Did we find evidence for life? No, but we don't have the capability to know that it was there. We didn't even find any complex organic molecules, but that's kind of what we're going to do now. So this is what that place may have looked like. We don't need to go to extreme environments anymore on Earth. We don't have to go to the high pH areas, the low pH areas, the boiling hot areas, and find extreme environments. We found a place on Mars that was so benign, as I said to the press, if you were having a hard day in the desert, nobody was around, and there was a glass full of water, you'd happily drink it. And so this is a place in Western Australia. Here's the Southern Ocean, and there's a kind of a rock that's weathering there that's just like the rock that occurs on Mars. It's called basalt. And the water, the rainwater, just percolates through this rock, and it comes out into these ponds, which get dry, and sometimes they're wet, sometimes they're dry. But if you dig into those ponds and take a shovel of that mud out of there, this more or less has the same composition of the stuff that we found on Mars. It's a really kind of an Earth-like environment. We just don't know about the life part of it, but we accomplished our principal mission goal. Okay, so a couple of weeks after we landed the sky crane successfully, the mission was covered by time. And the point of the article, if you were to read into it, was what do we learn from a rover that's at that time 154 million miles away? And if you go into the article, this is the thing that really impressed me, that I sort of took away from that, is that what we saw happening with the transformers and the things blowing up with the laser and all the rest of that is that people just enjoy this, and it doesn't make any difference about what your position is about the value of science. It's just we're good at this, and once in a while the government gets it right. I would say back in probably 2009, we probably had 4,000 people on the payroll. That was just at JPL. In addition to that, we probably had 3,000 contractors and subcontractors that were all supplying parts and hardware and labor to help make this mission happen. So it was a tremendously collaborative effort that obviously has achieved a pretty high level of popularity. Okay, I want to come back to Roy Chapman Andrews. What are we going to do now? So, here's his Flaming Cliffs locality back in 1923. And after these discoveries, he went back and became the director of the American Museum of Natural History, but this is this famous dinosaur egg discovery. And what he learned to do by going back to that different planet in Mongolia was to basically how to explore for something systematically when you can't cover the whole world. So this is the Flaming Cliffs. This is this famous location where these things were discovered. Kind of looks like Mars. Got red rock, it's got layers. But the important thing for dinosaurs is that dinosaurs make hard parts. Microbes don't. That's the hard part. That's the difference here. So even though you have the kind of sediment, it's not exactly a thing we're looking for Mars. It works real well for dinosaurs. But here's the difference between where we've been on Earth and where we need to go now for Mars. Going onto Mars is like going back and exploring for life on Earth billions of years ago. This is what we're all trained to think about as kids that go into science and professionals that think about science, is that you've got hard parts. And the dinosaur, all the skin decays and goes away, all those organics disappear, but the bones stick around and leave skeletons behind. And that's what we're used to exploring for. But the problem is, in the world of modern paleontology, if you go back and you ask, how do you find evidence for life on Earth before any fossils were around, any hard parts, they're basically chemical fossils, chemofossils we call them. So you have complex organic molecules that may represent the structure of the membrane of a cell, but then if you add water, let the water stick around for a while, convert the sediment to rock that the microbes are in, it gets degraded and you form much more simpler organic molecules to look for. But that's the trick for us. And if they go into the wrong environment, if they go into that highly oxidizing red environment, these molecules will break down into mostly CO2, go away as a gas, and there could have been life on Mars and you'd never would have known it. So the problem is, even on the early Earth, on a planet that's teeming with life, we almost never see it preserved. So the challenge for us now is we've demonstrated that Mars can be habitable, at least in one place, at least at one time. The challenge now becomes to try to find where to go to find the remnants of organics that might have been there if there had ever been life left behind. So I'll just finish up with John Wesley Powell. You go see this picture on the 4th floor of the building. I was walking along and I thought this is the perfect place to show this because that's what these guys were doing back in 1869. They're here, they're in the inner gorge of the Grand Canyon. And just above the inner gorge are the layers of the Grand Canyon. And at that time, nobody knew what the story of life was going to be on Earth. There was no way to know that going up into those layers you would find evidence of life, but that's what Powell did. And in his second mission, he had a paleontologist along who found the first trilobites in Western North America in those layers. So for us, it's kind of the same thing. We're not in boats, we're in a rover. And we go into these hills, maybe a year from now we'll be there, but that's the idea, is to basically turn these pages in the history book of geologic time on Mars and see if we can ever reconstruct an ancient environment that not only was habitable, but may have also preserved organic carbon. That's our goal. So thanks for listening.
Thank you very much. We have time for some questions.
Sure.
You have 2 microphones going around. Please stand, state your name, whether you're a member of the society or not.
My name's Gary Peters. I'm not a member of the society. Just one of your final comments. Why will it take you a year to get to Mount Sharp? If you know that's your next goal, why will it take a year?
Yeah, unless we find something else interesting along the way. So we can do enough mission planning we know enough about the autonomous navigation system, and with all the satellites, we're able to make digital terrain models that would probably see some of the people sitting in the room here. So from that, then we can calculate the speed at which we can drive, and we have probably another month or 2 of work where we are right now we're satisfied with that. And then when we start driving, we have to go at least 10 kilometers to get to this particular place, so it just takes that much time. Yeah.
Bob Terry, yes, I'm a society member. I was curious, when the Mars One organization puts boots on the ground in 2023, what do you think NASA will learn from them?
Well, 2023, I hope we're getting the vehicle up there that's going to teach us how to get samples back from Mars, because the thing that we've gotten pretty good at is landing on Mars, but now you have to figure out how to get away from that gravity. So you got to build a lot of hardware and get it up there, and sample return is a good place to begin with that, because it'll be easier to do than humans.
My name's Rudy Krutar. I'm a member of the Society. And I have a philosophical question for you. You talked about what appears to be magic to many people is simply advanced technology. And I've noticed that that what we consider artificial intelligence has changed over the years and the decades. What do you consider that when you began your career in Mars rovers was artificial intelligence is now not considered artificial intelligence? Well, how has artificial intelligence changed, and what is now artificial intelligence in the Curiosity?
It's a good question. It's a hard one to answer, because our design principles, we're very nervous about trying the latest and greatest thing. I mean, it's a bit paradoxical, but the CPU on the computer is still using the RAD 750 chip. I mean, if something works well once, you probably don't want to mess with it unless you have to. We would have done airbags for this mission unless the mass of the rover was so great that we knew that there was no material that would withstand that force. So with AI, the issue there is that the onboard autonomous navigation for the rover is actually based on a pretty simple principle, which is just stereo parallax from the two cameras that have about the same separation as your own eyes do. And so we try to calculate where objects are. So the most advanced thing we would do is, like in this terrain that you see here, if the rover was here, we can see that it's relatively flat. And that part, we do what we call a blind drive. That's where you use human judgment to say, I know I can make it at least half the distance to the edge of the platform, but then after that I got to... And then the AI comes in, and you move a half a meter, you take a pair of pictures, they compute a digital elevation model of the terrain, then you move another half meter, take another set of pictures, compute the digital elevation model, difference the two, and if the difference exceeds some threshold value, then the rover shuts down autonomously, and it sends back an error command that says that there was an obstacle in the way. And so as much as it seems like for these missions we should be using a lot of that stuff, the fact is, at the end of the day, we're uncomfortable. And we'd rather still just use our own eyes when we only get one rover to make sure we just never make any mistakes that we wouldn't be responsible for as humans.
Well, computer graphics used to be part of artificial intelligence. No longer because we're good at it.
Right. Yeah. We're behind the curve. I can tell you that we like to be behind the curve on that.
My name is Mike Green, and I'm a member of the Society. In preparation for this lecture, I did a little reading, and I read on the web that they said that Mount Sharp may have been caused by the wind. Do you have any comment?
Yeah, so it's, we don't know what formed the mountain, and to be fair, for us, we don't really care how the mountain became the shape that it has today. The only thing we care about is that it eroded away and exposed these layers. We're interested in the guts of the mountain rather than the shape of the mountain. As far as the shape of the mountain goes, it's a big mystery. One model has it that the crater's a big bowl, it's a bathtub, and it just fills up with sediment. And then, unlike the Earth, the climate's dry. After it's filled up, all the water shuts off, and then for 2 billion years, the wind swirls and moves around, and then it just cycles around, and it erodes out the margins, leaving something behind in the middle. In the other end member case, the crater is not filled in, the wind swirls around, but as it swirls, it's got a slack spot in the middle where the sediment tends to fall out, not be moved by the wind, and so the mound builds up from the bottom up, and it forms kind of a haystack, and that's how it gets its shape, and we don't know. Those are the two options.
Other questions? You have a question? Okay.
What do you think about the very popular Mars immigration plan? I think it's kind of like a hoax, but it's run by some very credible NGO. So what do you think?
You know, it's a little bit like the question I was addressing before. You know, I got my heads in the weeds just trying to figure out how to do this. And, you know, for those kinds of missions, I'm just not involved. I don't have a strong opinion one way or the other. Yeah.
Tim Thomas, I'm a member of the Society. I'm wondering about the odds of finding a meteorite somewhere in your exploration of Mars.
Yeah. Interestingly, so far we haven't seen anything that looks like a meteorite, but with the Opportunity rover that drove forever across this broad flat plain, that's how we were able to go 30 kilometers. It's really flat. When you see a stone of any type out on the plain, what we realized after a while, the only rocks that stick up, and I mean you see these things a mile ahead, you just go to it and chances are it's a meteorite. And so in this case here, we have a lot of rocks that are coming in because the crater rim is very close by. I mean, we've never worked with a rover in a terrain this close to mountains before. And so what tends to happen is that the meteorites that are coming onto Mars, they hit the surface and then they send rocks that they've hit flying off. And so what we tend to find is what's called secondary impact ejecta. So far we haven't found any meteorites. I'm sure we're going to find one sooner or later.
Other questions? Yeah. Okay. Just a moment, please. Yeah, it's coming up. Oh, wait, just wait. It's coming up. Oh.
Yeah. Hello, I'm Adrian Southard. I'm not a member. I wanted to ask about the other possible landing sites. What did you lose out by not going to those? And what made Gale Crater the best?
So the short answer is that Gale sort of won the day because it had the greatest diversity. It sort of got the most number of buttons to push of different things. Two of them that we didn't go to were kind of the same, where there's a crater that looks like it had a lake in it with a delta, well-defined delta that goes into it. And so one of them is probably the best place on Mars where you could make the case that there was once a body of standing water. Here, with the alluvial fan, we had a pretty good guess from orbit that there was flowing water, but we didn't know that the water, maybe it was flowing along and then it just sieves through the dry sediment out in the front, and there was never a lake. Now it looks like we found something that looks like a lake. And then there was another site where there was a very high concentration of clays that if you would have landed there, almost any place you would have landed, you would have been able to sample clays. And so the one that was a delta was a real hot spot for people that wanted to explore what looked to be almost certainly an ancient lake. The one with the clays was a place where people would say, you know, this is definitely a place where we're going to find some clays. And the remarkable thing about Yellowknife Bay is that we found a lake and we found a rock that has more clays in it than anything that people had really imagined before for Mars. And none of that, well, the clays weren't observed from orbit. And we were nervous as we drilled into it. We weren't sure we were going to get anything. So I think it just underscores the fact that you know, there's some parts of Mars we're getting to know well, but we're still always going to get surprises.
Michael Hendrickson. I'm also a member of the Society. I wonder, sir, assuming that the cosmic ray bombardment on the Martian surface 3.5 billion years ago was similar as it is today, how would that have affected the evolution of microbial life on the surface, assuming there was a lot of water there or whatever at that time?
Right, good question. You know, that's actually the same question for Earth, because if you imagine that Mars once had a denser atmosphere that would have been equilibrium with all that water that would have been standing around, it would have been the same attenuation in the atmosphere that you have today. And so the idea is that evolving microorganisms have to evolve, especially the UV radiation. And if you just go down below the sediment, you certainly get away from the influence of the sun. And then for the cosmic radiation, if you go another meter or two, you get away from that as well. So I think many people are favorably inclined to want to think about the evolution of early life forms, even on Earth, as something that doesn't have to happen right at the surface. It could happen slightly below the surface and protect itself from radiation.
Hi, I'm Carl Merrill. I'm a member of the Society. Could you comment on the various reports of methane on Mars and how Curiosity is equipped to look at this issue?
Right. Yeah, I didn't comment really on anything that has to do with the atmosphere, but we've made 3 measurements, and in each case, the threshold of detection for our instrument is about 3 parts per billion, and we have no positive detection. So that doesn't mean that there isn't methane on Mars, but it means that if it's there, that it's below the detection of our instrument. In the next couple of months, we're going to be able to do what we call an enrichment experiment, where we can actually suck in the air and compress it a little bit, then also pass it over scrubbers and getters that get other gases away, so that we have the best chance to exaggerate the signal of methane.
Any other questions? Okay.
Have you guys considered open sourcing some of the engineering plans and the operating system and whatnot? I mean, obviously you're not going to find the radiation hardened chips, but I think it would be cool if you did that. Somebody would probably make a duplicate rover in like 6 months or so.
Yeah, I was telling somebody earlier tonight that if this computer was to disappear from the room, I would be liable for a felony offense, just because some of those plans, there is what is considered to be government proprietary information. It goes way above my pay grade, those decisions. But there is definitely something to be said for releasing stuff, and we do. So all the images, we release those as fast as they come down to Earth. All of our science data basically comes out in 3 months, which I think is fair, because it gives the scientists that work so hard to get it, give them a chance to get going. But if they don't respond fast enough and they're not doing due diligence, it will eventually go out to the public. But the engineering data, that's a tougher one.
My name is Jane Stout. I'm not a member. I found the landing process to be very interesting, and I'm wondering if you have a plan to bring the rover home ever, and if you care to discuss that.
We'd love to bring it back to the Smithsonian. That might be a good sort of technology demonstration for the Mars sample return. I mean, the great challenge for getting humans to Mars is dealing with gravity. I mean, we can build a spacecraft in low Earth orbit and send it to Mars, and we could probably get it to land, but then you have to have somebody that will ascend from the surface. So, sending back a ton of mass, that'd be hard to do. But that's basically, most of these things are on a one-way trip that we know of now. Doesn't have to be that way, though, in the future.
Okay.
Thank you. Name is Andrew. I'm not a member of the Society, at least not yet. I wanted to ask if you could comment a little bit more on the instruments and the technology on the rover. Like you mentioned, it's parts per billion sensitivity and so forth. What are some of the new techniques that you look forward to using? You mentioned the drilling one, which I thought was very interesting compared to the previous one. Just go into a little detail about that and some of the ones you were very excited on.
Yeah. I'll just single one out. I mean, we can, if you want to talk more later, but like the X-ray diffraction unit, that has a sensitivity of about 1%. So we can take the rock, we can take the powder, put it into the X-ray diffraction unit, and we can quantitatively assess everything that's in that rock that's more abundant than 1% of its total mass. And you can do better on Earth. You can always do better on Earth, but for something that's as big as a toaster, that's pretty darn good. And then what I didn't get into the details were in the SAM instrument, which is the microwave oven for 90 million. That has a quadrupole mass spectrometer in there, and basically we use that by taking the rock powder, putting it in an oven, And it goes up to 800 to 1,000 degrees centigrade, and as the powder is baking away, all the volatiles are coming off. So that's how we know there's carbon in the rock, because at about 350 degrees, we suddenly see a spike rise in the amount of CO2 that comes out of the rock. So I don't know if you do this stuff for a living, but if you don't, the way I like to explain it is it's like baking a cake. You walk into the room, you know there's a cake in the oven because you smell it. And what we're doing is we're collecting those gases, and each one of those gases tells us about what's in the rock.
Any other questions? Well, I guess, but thank you very much. Well, first of all, I have two things for you. First is the announcement of the lecture, signed by the members of the General Committee and framed for you to keep.
Thank you very much.
And
oh boy, signatures.
Yes. And the second commemorative piece is the dinner lecture announcement, framed as well, for you to keep. So that's for the 82nd lecture.
Thank you very much.
Thank you very much.
Thank you.
Okay. Just transport them. Okay. It's getting a bit late, but actually that was a very, very, very informative and interesting lecture. Thank you very much. And the speaker, of course, will be around during the social hour to answer any more questions. I'm sure some of you will have